Research establishes a strict physiological ceiling. An operator can meaningfully process a maximum of one alarm per minute before cognitive overload sets in. But during an upset, that rate abruptly spikes to 40 alarms per minute, multiplying to 10 times what the brain can handle. This is a chronic reality across manufacturing. A typical automotive assembly plant generates between 3,000 and 5,000 alarms in a single shift. Operators meaningfully acknowledge less than 15% of those notifications. The remaining majority are simply nuisance alerts, stale data, or downstream cascading effects that completely bury the genuine critical signals. The global smart SCADA alarm management market reached $2.5 billion because the industry recognizes this data overload. Yet, heavy investment in alarm software has not solved the underlying cognitive bottleneck. When essential data is buried in noise, the outcomes are severe. At the BP Texas City refinery in 2005, key-level alarms failed to successfully notify operators of unsafe conditions in a blowdown drum. 15 people died and 180 were injured. The tank overflow fire at the Buncefield oil depot caused over £1 billion in damage. The high-level safety switch existed, but the necessary warning did not reach the operator in time to halt the flow. Traditional alarm management rationalizes the database by adjusting thresholds and suppressing nuisance alerts. It reduces the noise volume, but it operates purely as a reactive structural intervention. Rationalization tells an operator that a threshold has been reached, but it provides no frictionless way to query the historical data to understand exactly why. To understand this failure, we map the legacy control architecture. Field equipment generates raw data. That data feeds upward into two separate systems: the SCADA interface, which displays live process values to the operator, and the historian server, which archives the long-term operational record. The historian is a highly specialized repository of context. It contains the long-term trend analysis and equipment history necessary to diagnose complex anomalies. However, accessing that context requires a multi-step manual process. The interface is distinct from the primary control screens, separated by specialized database procedures that require engineering mediation. Executing a query requires knowing the precise, often deprecated, tag naming conventions for specific sensors, selecting the correct historian client software, and navigating complex user interfaces. Even on a good day, retrieving a single comparative trend takes 15 minutes. Consider a compressor where the discharge pressure drifts 15% above its baseline. It hasn't breached the alarm threshold, but the reading is abnormal. To investigate, an operator must pull 6 months of historical data, manually hunt for identical drift patterns, and check what physical failures correlated with those past events. At 2:30 in the morning, the specialized instrument engineer who knows the tag structures is asleep. The two operators on duty cannot dedicate a quarter of an hour to wrestle with the database client while actively monitoring the rest of the facility. The physical architecture of the legacy system forces the operator to abandon the data entirely. They are forced to make a judgment call based on intuition instead of empirical evidence. That reliance on intuition is rapidly becoming a liability. The industrial workforce is experiencing a massive demographic shift as a generation of veteran operators retires in large numbers. A 30-year veteran possesses deep, undocumented pattern recognition. They know exactly which subtle sound from a pump or which slight deviation on a trend line requires immediate action, effectively interpreting the field equipment directly. A new operator, 6 months into the role, lacks that internal database of experience. Their entire situational awareness is limited to what they can extract from the legacy SCADA screens. Deloitte projects that U.S. manufacturing will require 3.8 million new workers by 2033, and nearly half of those roles may remain unfilled due to skills gaps. Over 70% of the United States power grid is at least a quarter-century old. Running decades-old legacy equipment requires historical context that incoming operators do not yet possess. When a new hire encounters a strange reading, they cannot instantly verify if it's a known, acceptable edge case or a critical warning sign. The data exists in the historian, but it remains isolated behind technical layers they haven't learned to navigate. Without the accumulated intuition of departing veterans and blocked by the high friction of data retrieval, the incoming workforce lacks the tools to run legacy facilities safely at their operational limits. This gap requires a specialized intelligence layer. An agentic AI acts as a bridge, querying the historian data through plain language. The software connects natively to existing operational technology protocols like OPC-UA and Aveva PI. It interprets the existing infrastructure rather than requiring large-scale data migrations. Because this is a critical infrastructure environment, the architecture operates under a strict air-gapped on-premises mandate. It has zero cloud dependency and zero latency introduced by external servers. The agentic layer is heavily constrained. It operates strictly as a read-only analytics tool. It cannot actuate valves, modify set points, or execute autonomous control over the plant floor. The queries maintain lossless data fidelity. Standard large language models often summarize and hallucinate over datasets, but this architecture retrieves exact, unsmoothed historical records to ensure subtle anomalies remain visible. For a night shift operator, this means they can ask a complex data question in plain language and receive a direct answer within seconds, completely localized on the plant network. By eliminating the need for tag memorization and specialized client software, the operator shifts from struggling with database syntax to making immediate strategic decisions based on verified plant history. To measure the operational impact, we examine a process trip, a sudden equipment failure that triggers an immediate shutdown sequence. Within 90 seconds, 40 distinct alarms fire simultaneously. The operator is instantly pushed to 40 times their cognitive processing limit. In the legacy workflow, the operator must first physically acknowledge the alarms to stop the console from locking up, burning valuable time just to manage the software interface. Then they manually cross-reference dozens of screaming alerts to separate the single root cause mechanical fault from all the downstream cascading effects. This diagnostic process typically consumes 12 minutes of critical response time. With the conversational AI layer in place, the operator types a direct, natural language query asking for the first abnormal reading that preceded the trip, and which current alarms are merely downstream effects. The system instantly cross-references the live alarm log with the high-fidelity historian data. It pinpoints the exact initial deviation and visually separates the true root cause from the noise of the cascade. A process that demanded 12 minutes of high-stress manual correlation is reduced to a 15-second data retrieval task. The operator gains immediate prioritized situational awareness, allowing them to initiate the correct recovery protocols well before the cascade results in catastrophic equipment damage. Alarm rationalization remains a foundational engineering requirement. If a system is chronically flooded with nuisance alerts, facility engineers still rely on ISA 18.2 protocols to adjust thresholds and suppress bad data at the source. This equation illustrates the complete solution. Rationalization suppresses the volume of noise, while the agentic layer provides the immediate access to historical context. Stripping away the technical barriers of archaic historian tag nomenclature empowers every operator to interrogate the system, regardless of their tenure. Because the system supports voice-based queries, a technician standing on the physical plant floor with both hands occupied can access decades of operational history without ever returning to the control room workstation. Plant operations are no longer bottlenecked by the availability of a single specialist gatekeeping the historical database syntax. Agentic AI provides a direct line to plant data. By answering questions in seconds rather than hours, it scales the power of human intuition across an entire transitioning workforce, finally closing the gap between alarm fatigue and definitive answers.